Swayam Prabha. Digital India. Educated India.
Dear students, welcome to our next discussion on Simplex method. In our earlier lectures, we have looked into methods to solve optimization problem using the concept of Lagrange multiplier, as well as we looked into earlier formulations of unconstrained programming. And now we will move to a very special set of methods, what we call as linear programming problems, and that we will try to understand how to solve these through Simplex method. If you recall, in our previous lecture, we already introduced the linear programming problems, where they are used, how many infrastructure management problems can be framed as linear programming problems, and what are the advantage of linearizing a system over the nonlinear methods. But in previous discussions, we never looked into the specifics how to solve the problems using Simplex method. So we will begin our discussion with a brief history of the Simplex method. So this method is also known as Danzig method, named after the engineer who discovered this particular method somewhere in 1947 during World War II. And purpose to create this method was to solve large-scale linear programming problems arising in military logistics and resource management. In fact, there are many interesting articles that have been written about Danzig and how he thought about linear optimization as one of the solutions during the wartime, when it was needed the most by the fighting armies for resource allocation. And it was of course used for optimizing resources and planning. And the key contribution of this particular method was that it's a very efficient algorithm, and we'll learn the reasons behind its efficiency and how it actually works. And it also provides a systematic procedure for traversing the extreme points. In our previous lecture, we learned that whenever we have our constraints written as linear equations, we are essentially looking at the convex regions, and the solution or the most optimal solution would always be at the extreme points of the convex region that we will trace. So this method is also known by the name of simplex algorithm, and sometimes we also call it as a corner point method, as we will move from one vertex to another in search for our optimal answer. So simplex algorithm was a great start, and it is still used widely across various algorithms or programming languages that solve optimization problems. But various refinements have happened to improve its computational efficiency, and methods such as revised simplex method, Karmakar method, dual simplex method, and primal dual algorithms have been proposed. We will also look into a few of these in the context of infrastructure planning and resource management. But today our focus is going to be on the simplex method. So let us quickly recap what is the key philosophy behind linear programming problems, and the same philosophy also applies to simplex method. So the key idea behind simplex method is to exploit the convexity of the feasible region. So as we learned in last class, that if you have two constraints, one drawn in orange and another one drawn in blue, and both of them have their feasible regions, let us say marked by the region that I am now shading in blue. If we have to meet both of these constraints, or we will call this as equation 1, and we will call this orange one as equation 2, and we have to be on the uh, side which is less than equal to both of these constraints. So the blue one would come out to be the region of interest, and this is going to be a convex region, because if we draw any line in this region and join it by the straight line, it is always going to be within this particular region, and hence ensuring its convexity. So we also learned that whenever feasible region is convex and is bounded by a hyperplane, and in this case the hyperplane is the line itself, as we are talking about the two-dimensional space, the optimal solution would lie at one of the extreme points. So optimal solution would be either here or here or here or here or here. So out of these 5 points, we already have our candidate solutions, and one of them is going to be the optimal solution. And in simplex method, what we do is that we start from any of the feasible extreme point, and then we move along the edges like this, and so on, until we reach to our solution, which is the most optimal. Now, in case of two-dimensional setting like this, we would have finite number of extreme points. But think of a situation where you are dealing with 500 variables, or sometimes even more than that. Traversing across all the extreme points is not going to be an easy task, and it's going to be computationally very inefficient. That is why algorithms such as simplex methods come into picture to make our lives easier and take us towards optimal solution at much faster rate. So what we will do, we will find a way to go from our extreme points in much faster way, that we don't necessarily have to go exactly in some rounding sequence going through multiple non optimal points, but we will find a way to go from, if this is our starting point and hypothetically speaking if this happens to be our extreme point, we will try to go here either directly or through the shortest path, or relatively shorter path than traversing across all the points. And what we do is that at each step we choose the adjacent extreme point that improves the objective function value, and this entire idea and methodology together would give us the simplex method. We already have emphasized, and I think I should re-emphasize, because convexity plays such an important role in linear programming problem, that the simplex method derives its strength from the role of convexity, that is intersection of linear constraints always form a convex polyhedron, that we already saw, and it also ensures that no local maxima or minima other than the global maxima or minima, and optimal solutions will always occur at the extreme points, and we will systematically move from one extreme point to another point in the search of our maxima or minima, of course, because maxima and minima are interchangeable by use of negative sign. Now, if we state a linear programming problem in a standard form, it would look something like this, that we have to minimize our objective function z, c transpose x, where c is a vector of coefficients and x is the vector of our variables of interest. Again, x vector can be written as x1, x2, all the way till xn, and it is subjected to m number of constraints. And there is another constraint on all the variables itself, that all of these have to be greater than 0. So this is an important constraint that we have to abide by in all the solutions. So if this constraint is violated, then our solution is not going to be feasible. So we would be using this word called as feasible solution quite a lot in simplex problems, and feasible solution is essentially those values of x that satisfy all the constraints while ensuring that none of them have value less than equal to 0. If a situation arises that where your variables are indeed less than equal to 0, we also have a way to work around that and convert them to positive values, but we will worry about those special cases later. But the point that I'm trying to highlight here is that we can express any linear optimization problem into standard form by certain mathematical operations that we will learn in our subsequent discussions. So, while we are presented with inequality constraints, simplex method would work very efficiently, or in fact the standard procedures that you would see in various textbooks or in this particular lecture is laid out for equality constraints. So what we do is that we can always convert an inequality constraint, specifically less than equal to constraint, by adding what we call as a slack variable. Just to give it very simple explanation, let us say I have equation 3x plus 5y less than equal to 10. Now, if you ask me that, hey, can you convert this less than equal to constraint to an equality constraint? I can say, yes, certainly I can do that. But for that, I would need some other value or variable which is guaranteed to be positive, s greater than equal to 0, because LHS is less than RHS. It has to be less than or equal to RHS. But to make it equal to, I need to add some other positive number so that the LHS increases in its magnitude and match the value of RHS, which is 10 in this case. So the variable or the extra slackness I have added to this constraint would be called as slack variable. And if you notice, slack variable also has to be greater than equal to 0 if we have to really meet this requirement of uh, making both sides equal. So then what we do is that once we add the slack variable, our standard form now changes to that minimize or maximize. Again, this is interchangeable, so I would not worry too much about that, because we can also apply our simplex method to maximization problems as we would do for minimization problem, and subject to certain constraints. But now all the inequality constraints have been converted to a standardized form where this I happens to be identity matrix or identity vector slash matrix. In this case, it is indeed matrix because all the slack variables are introduced with one coefficient, and condition of x greater than equal to 0 and slack greater than equal to 0 also applies in this condition. So in after converting our problem to standard equality form, we would have n number of decision variables that were originally present in our question and m number of slack variables, one slack variable being introduced for every constraint that we are dealing with, as a result of which we are going to handle n plus m number of variables. So if n is equal to 2 and m is equal to 2, we are looking at total of 4 variables. The moment we do that, typically we will have more number of variables than number of equations itself, and that is where we may have to apply some concept of selecting certain variables to be equal to 0, because we can never solve a system where we have more number of variables than the equation itself. So for to do that, we would apply a, I should not say that it's a trick, but an approach, what we call as selecting certain variables as basic variables and certain variables as non-basic variables and find our solution. So what we do is that if we are dealing with more number of variables, then equation itself, and we are interested in the solution, what we do, we select certain variables as basic variables and certain variables as non-basic variables. I'll give you another very simple example because this is something that confuses students a lot. So let us say that I have two equations, one equation 3x plus 5y less than equal to 10. I say that convert it to standard form. You say, okay, I can say that plus s equal to 10. Now you have only one equation, but three variables are waiting, x, y, and s. You can say that I can never solve this particular equation because, I only have one equation and three variables. So to address this, what we do is that we force at least two variables to be equal to 0. So we can say that if y happens to be 0 and s happens to be 0, I get my solution x as 10 by 3. In this case, whatever variables I have forced to be 0 would be called as my non-basic variables. And the variables that we find the values for that are not forced to be 0 would be called as basic variable. And in this case, all our non-basic variable are set to be 0 and we get the solution to the basic variable because all others have been forced to be 0 and hence our problem now reduces to bx b equal to b because all others are forced to be 0 and b is called as basis matrix. So I can easily solve xb as b times b inverse times b, which is nothing but essentially separating the variables on one side and finding the values of interest. So we will of course deal with this mathematics more clearly, but this is essentially what we will do. We will move from one basis to another basis in simplex method, and we will always ensure that when we move from one basis to another basis, we are always moving from one corner point to other corner point in most efficient manner. And our objective function z would always be sum of the coefficients of basic variables multiplied by the basic variables plus coefficients of non-basic variable multiplied by the coefficient of non-basic variable, and this term would always be equal to 0 because by definition non-basic variables are 0 themselves. So objective function would only be influenced by the choice of the basic variables and the values they would take during our objective. Again, we'll not worry about exact mathematical construct of basis matrix right now because as we will solve the problems and dive deeper into understanding of simplex method, lot of things would get clearer because we will find an algorithmic way to take these inverse and do these simplifications. So we will not worry too much about the exact mathematical uh, definitions at this particular point. Now, even if we don't have to worry about this exact mathematical construct, one thing that we may have to internalize when we are dealing with simplex method is that we always have to force at least m variables to be non-basic or to be 0 if we really want to solve our system. Now, if we talk about m variables to be selected out of n plus m, one question should organically arise that if I have n decision variables and m slack variables that I have introduced, and the slack variables that I have introduced I am representing by S1 to Sm, which variables I should select and force to be 0? You can say that we can randomly select any of these variables and force them to be 0. But what may happen is that if we make that choice randomly, we may drift away from optimal solution. And it may take long time to converge to the point of interest or extreme point of interest. For example, even for such a simple case, when we are dealing with 10 variables and m equal to 5 constraints, we are looking at more than 3000 possibilities to have the basis or forcefully non-zero variables. So evaluating all basic feasible solution is indeed impractical for us because if you have n plus m variables, you have to actually force some n variables to 0 and so on, so that you have m number of non-zero solutions available to you. Also, when I say non-zero solutions, I'm not saying that the basic variables cannot assume value of zero. They can, of course, during optimization can take value of zero, but I am not forcing them by choice to be zero as I'm doing with non-basic variables. So to address this complexity or combinatorial complexity, what simplex method does is that it moves from one basic solution to adjacent basic feasible solution by ensuring that the objective function only improves as we go from one extreme point to another extreme point. This is done by exchanging one non-basic variable with another non-basic variable. So I'll just go back to the slides. And at each point, we will update the coefficient table. We also call it as a tableau using various shortcuts that we will learn. These shortcuts are nothing, but these are row and column operations that we used to do on system of linear equations. And to speed it up, we would find some again algorithmic way to do this particular part faster. And we will, of course, be able to find the optimal solution without exhaustively searching for all the bases to find these solutions. So let us try to understand this with help of a problem. That our problem that is given to us is maximize z equal to 3x1 plus 5x2, and it is subject to two constraints: x1 plus x2 less than equal to 4, 2x1 plus x2 less than equal to 5, x1 and x2 are greater than equal to 0. So if you just focus on this problem, this happens to be a problem in two dimensions. I can easily take a graph paper, make the graphs and solve this. However, we are here to learn more generalized cases. What if this problem happens to be n dimensions? Then you can never use a graph paper and find your answer. So that's where we have to really learn some mathematical way to solve that. Now, one thing is clear, that if this would have been a problem of unconstrained optimization, that is, imagine that these constraints are not given to you and you are just focusing on 3x1 plus 5x2, you would say that x1 should tend to infinity or should be a very, very, very large number. X2 should also tend to infinity. My value of z would also tend to infinity, and I have maximized this problem. You are absolutely right. Or x should increase, x2 should increase if from 0 values towards infinity to increase value of this function. However, what is preventing our scaling to infinity are these two constraints that are present. First one being x1 plus x2 less than equal to 4, and second one is 2x1 plus x2 less than equal to 5. So let us say that I make x1 5. I would immediately violate this constraint because x2 is not allowed to be less than 0. So what does that mean? That even if we want to go from 0 towards infinity, during this process, I may start violating constraints, maybe one constraint 1 or constraint 2 and so on. And that is essentially going to limit the scaling all the way to infinity. So we can only introduce a variable and make it a basic variable only up to a point so that other variables do not fall negative. And this is going to be the premise of our addition of entry variable or exit variable. So as we proceed towards understanding simplex method with help of an example, we introduce two slack variables to convert our inequality constraint with equality constraint. So it becomes x1 plus x2 plus s1 equal to 4, 2x1 plus x2 plus s2 equal to 5. So now we have two decision variables x1 and x2, and we have two slack variables s1 and s2. So initially, whenever we initiate the simplex method, what we do is that we set our slack variables as basic variables and force our decision variables to take the value of 0. The utility of this would be very clear once we start talking about the tableau, because the moment we do that, you clearly see that how tableau would look. The coefficients of first equation as 1, 1, 1, 0, second 2, 1, 0, 1, because then it becomes x1 plus x2 plus s1 equal to 4, 2x1 plus x2 plus s2 equal to 5, and minus 3 minus 5 equal to z. So what we do is that we have the original constraint objective function as 3x1 plus 5x2. So we say that z minus 3x1 minus 5x2 equal to 0. So this is equivalent. You can always say that 3x1 plus 5x2 minus z1 is also equal to 0. Nothing wrong with that. But the advantage of writing in this form is that whatever is the value we will get here is going to be the optimal value of z without any sign change. But when we solve more questions, all these details will become very trivial for us to even worry about, because we would understand how this is actually working. Now, when we make S1 and S2 as two basic variables, so I would say that S1 and S2 are my basic variables, then X1 and X2 are bound to be non-basic variables, because I have to select out of n plus m, I can take only two basic variables which I have already selected as slack, and both n would be selected as the non-basic variable, would take the value 0. Now when our x1 and x2 equal to 0, our objective function does take the value of 0, and we can certainly do better if this is a maximization problem. What is the best way to make this 0? This better than 0 is that we start increasing value of x1 and x2. Now to increase the value of x1 and x2, we have to move one of these, x1 or x2, from non-basic variable vector to basic variable. And if we make one of them non-basic, either S1 or S2 have to be made non-basic variable, which originally happened to be, these are originally basic variable. And it is very clear that if I increase x2 by 1 unit, I am going to increase my objective function by 5. If I increase x1 by 1 unit, I am going to increase my objective function by 3, and I can only increase one at a time. So organically, I should select a variable which has higher coefficient if I am looking for maximization problem. So in this case, I have only moved it on the other side, but magnitude wise, this remains to be the highest. And if I have written my objective function in this form, I should choose that particular variable as an entering variable that has a larger negative coefficient. So in this case, I would introduce x2 as a basic variable and would have to ask one of the S1 and S2 to leave. I would annotate this as entering variable. Now, who should leave? That variable that would hit 0 first. As I increase my objective function value by increasing x2, should automatically become the basic variable and leave the system. So if I go back to my constraints, if I increase x2 first, it is very clear that equation number 1, in equation number 1 is that x1 plus x2 plus s1 equal to 4. This is 0. And in second case, 2x1 plus x2 plus s2 equal to 5, and this is also equal to 0. So this reduces to x2 plus s1 equal to 4 and x2 plus s2 is equal to 5. If I start increasing x2, my s1 is 4 minus x2 and s2 is equal to 5 minus x2. If I increase x2, it will only take me 4 units to reduce S1 to 0, and it will take me 5 units to reduce S2 to 0. So S1 would be ready to leave the basic the basic variable space first, then S2. What I'm also looking at is that what I called as quote unquote shortcut is that if the ratio of RHS to the corresponding coefficient in the entering variable column is the smallest, that is going to be the first variable to leave. So 4 divided by 1 is 4, 5 divided by 1 is 5. So this happens to be the smaller value here. So this is going to be the variable that will leave first. Also mind it that we would only take the ratios with the positive signs here. So if x2 supposedly have a -1 coefficient, then if we go back here, that x2 is equal to 4 minus s1, and if this happens to be a negative coefficient, there is no worry anymore that if you keep on increasing value of x2, it can never happen that s1 would hit a negative value. So we need not worry about that. So all these ratios would only be computed with the positive values of the coefficient. This entire operation is called as the entry variable, exit variable, and pivoting operation, because we would always try to keep the coefficients of basic variables equal to 1 only in one equation. What it does is that, so here my basic variables were S1 and S2. So their coefficient was 1 at only one row, and second is take value 0. So I can immediately see that value of S1 equal to 4. In second case, I can immediately see that value of S2 is equal to 5 because its coefficient is equal to 1, and the RHS corresponding to that is 4 and 5 respectively. So if the coefficients are indeed 1, I can readily read the value as 4 and 5, because these values are not interfering with my solution because they are already forced to be 0. And to ensure that we always end up in this form, that where basic variable is equal to 1 only once in one equation, is achieved by the operation what we call as the pivoting operation. Pivoting operation is nothing, again as I said, it's the row transformations applied to the system of equation that we have dealt widely whenever we talk about solving these particular equations using just making sure that the coefficients are 1 and so on, by ensuring that all these equations are expressed in the most linear independent form as possible. And here, rather than doing this handling system of equations again and again, we will learn something called as an easy method to update the coefficients efficiently. So whatever we have learned, a quick summary of that, we will select the entry variable which has the most negative coefficient if my problem is maximization, and my objective function is written as minus a2 x2 minus a3 x3 and so on. So in fact, I should say plus, because then I'm not counting for the negative sign 2 times. So in this case, minus 5 is going to be the entry variable, and we will decide the exiting variable or leaving variable by looking into the ratio of RHS to the coefficient of x2, which is entering variable in this case. And one with smallest non-negative ratio would be the first one to leave, and in this case S1 will leave our solution. Now, as we decide on which variable to enter and which variable to leave, what may happen is that in that process our canonical form may get changed because of entering or leaving of new variable. So what we have to ensure that we update the value of all coefficients of basic variables in such a way that canonical form of our system of linear equations is preserved. What we mean by preservation of this canonical form of linear system is that, if you recall, earlier I mentioned that for basic variable S1 and 0 S2, and it was 0 S1 plus 1 S2, when we were talking about these two slack variables being introduced, all other variables were non-basic anyway, so their value was 0. However, for basic variable, we see that in one of the row, only one basic variable has coefficient 0 and other one is having coefficient as 1 and other has coefficient of 0. Similarly, in second row, only S2 has coefficient of 1 and S1 has value equal to 0. So whatever is the value that we would have on right hand side, RHS, is going to be the value of S1 and S2 directly. So what does that mean? That as we are going from one calculation of W to another calculation, our values are automatically ensuring that answer of optimized values and the values of x1, x2, x3, so on, at the optimality is apparently directly visible to us. And to ensure that, what we do is that we keep on applying some sequences of row transformations to ensure that we always have this canonical form. And to speed it up, we notice a pattern that we are going to discuss in our subsequent topics or slides as we move forward. So here is a problem that we would use in this case that I have already stated, that our objective function is to maximize 3x1 plus 5x2 and it is subjected to two constraints. And then we will see that how Tableau method can be framed for the problems such as these. So what we will do, we will just sort of resize this and put it in the smaller corner so that we have some space to work. Now in this case, I can make a tableau such that I include the information of the coefficients in this table and information about variables on the top. We will only do it once, and it would also sort of save some time in future. But if we really understand how we decide these in entering variable and leaving variable. So here I am going to have the variables x1, x2, s1, s2, and here I am going to have right hand side values written for us. So this is for basic variables, and first basic variable I introduce is s1 and second variable is s2. That would come by converting this problem to standard form, that is s1 equal to 4, 2x1 plus x2 equal to 5. You see that if x1 and x2 are chosen as the non-basic variable, I only have a coefficient of 1 at a time in each row, and hence we can say that this form is indeed canonical. So when I write the coefficient values, x1 is 1, x2 is 1, s1 is 1, s2 is 0. In next case it is 2, 1, 0 and 1. I will also write the coefficients of objective function. So I would say z equal to minus 3, minus 5, and slack variables are not present in the objective function. And to begin with, value of objective function z minus 3x1 minus 5x2 is equal to 0 itself. Why? Because x1 and x2 being our non-basic variable take the value of 0, making z equal to 0 as well. So when we talk about value of S1 and S2, they simply take the value 4 and 5 because these are the only two basic variables that are present in the solution. Now, we learned that we select the entering variable based on the fact that the one that would have maximum negative coefficient if our objective function is written in this particular form, because we already learned that if I increase the value of x2 here, my objective function is going to increase 5 times faster in comparison to a 3 times increase if I increase the value of x1 by 1 unit. So this is going to be an entering variable. I will highlight my entering variable in some green color. And to decide the exiting variable, I can simply look into that particular variable or that basic variable that would reach value equal to 0 first as I start increasing my value of x2. And we learned that that will happen uh, when I make the value of x2 as 4, s1 would be 0. And in this case, S2 would continue to be have a value of 1 or a non-zero value as I increase the value of x2. So in this case, S1 apparently is going to be the first variable to leave. For that, we also defined what we call as the minimum ratios. So we will define something called as minimum ratio here. And this number ratio comes out to be RHS divided by the highlighted corresponding element and 5 divided by 1, and here this still remains to be 0 because we have not updated anything. And whatever is the positive minimum ratio here, that is the variable that is going to leave our solution. So in this case, S2 will leave and become non-basic variable. Now, the moment it happens, we have to bring in x2 into picture in place of x1. And now x2 should be in canonical form. Canonical form. However, it is not happening now. Why? Because the coefficients are not of exactly just 1 at one place and 0 elsewhere. Also, we have to increase the value of x2 from 0 to some non-zero value. And how much we can increase? Only up to a point that S1 becomes 0, because S1 has to be always greater than equal to 0 on the condition of introduction of slack. When we edit that slack, we added a condition that S1 has to be always greater than equal to 0. So what we essentially do is that we apply the series of row transformations and change the values of all the coefficients while ensuring that basic row transformation operations such as R1 becomes R1 minus 2R2 or R2 becomes R1 divided R2 divided by 2, etc. These are just example, are maintained while ensuring that the integrity of original equations sustains and canonical form starts appearing. So in this case, we apply a very simple trick here, that is for all the elements outside highlighted columns and rows, we would say that their updated value Aij would be their original value minus the value that we see in their corresponding row. So in this case, we see this particular value as A highlighted row multiplied by A highlighted column divided by pivot element. And we would define pivot element as the element lying at the intersection of this highlighted row and highlighted column. So in our case, this 2 would be updated to the value of 2 minus 1 into 1 divided by 1, or it simply becomes 1. Mind it, this operation is only applicable to the points that are outside these highlighted rows and column. So 0 would be updated to 0 minus 1 divided by 1. This one would be updated to 1 minus 0 into 1 by 1. So this entire term would still remains 1. This 5 becomes 5 minus 4 divided by 1 equal to 1. And this minimum ratio we would not worry about. We would also update our coefficients. So minus 3 would become minus 3 minus into minus 5 into 1 or 2. This 0 will become 0 plus 5. S2 again will become, so the coefficient of S2 will become 0 because on top of it exactly 0 is sitting, and RHS value will become 20 because 4 times 5 is 20 and this negative sign becomes positive because of 1 minus is already sitting outside. So if this calculation is clear to us, we would have an updated tableau, and then we would be again repeating these calculation until we are left with no negative coefficients here. Also, one more thing that we have to also update these highlighted rows and columns. Since this is going to be in the pivoted form, so what would happen is that the all the values in the highlighted row would be divided by the pivot element. So this becomes 1 by 1, 1 by 1, 1 by 1, 0 by 1 and 4 by 1. And all the coefficients in the entering column or the pivot column becomes 1 at the point where new variable is entering and 0 elsewhere. So we should write our updated uh, tableau after updation of all the coefficients again to avoid any possible confusion. So I'll just make this tableau again real quick. I would recommend that as I'm doing it, you should also do it so that you understand how to update and write these particular tableaus, because that is going to be essence of this entire simplex method. So what we will again do here is that now we will add the new incoming variable as our basic variable, which is x2, and this remains as s2. We have x1. Just to save some space, I will say x2, s1, s2 and RHS. So after updation, the coefficients become 1, 1, 1, 1, 1, 0 and RHS happens to be 4. Similarly, S2 2 was updated to 1. This became 0. After that, I have minus 1. Then I had 1 and RHS. This 5 also became equal to 1. And when I talk about the objective function itself, z, the first coefficient becomes 2, next one becomes 0. Following that, I have value of 5, then 0 and 20. So let us also look into what we have, 1, 1, 1, 0, 4, which indeed is correct, 1, 1, 1, 0 and 4. For next row, 1, 0, minus 1, 1 and 1. So if we see 1, 0, minus 1, 1 and 1. So for our z, we should have um, after updation 2, 0, 5, 0 and 20. So what we get here is indeed 2, 0, 5, 0 and 20. So all our updations are correct using the formula that we have already learned as Aij new is Aij minus Ai pivot column into Ai pivot row j, A pivot element. So what we again did is that we updated all the non outside pivot row and column element using this particular formula. Then we normalize the pivot row elements by dividing each element by the pivot element, and update the objective function row similarly, whatever rules we are applying, and all elements in pivot column other than the pivot element becomes 0, and all these together form the step of updation of tableau in the simplex method. So this was our first row after normalization. This, after standardization, this is the one after standardization. Same for the second row. This is after updation. And this was our objective function before pivoting. So we applied the same operations on the objective function itself to get our updated values as 20, 50, and 20. So our complete updated tableau, what we wrote by hand, also looks similar and in these slides. And now we see that there is no coefficient that has a negative value anymore. So there is no way we can improve the solution further than 20. So the 20 indeed happens to be the optimal value, and we get this optimal value when x1 still remains outside our basic solution and hence a non-basic variable. So x1 equal to 0. We get the value of x2 directly as 4 from this particular column 4. We get value of slack S2 is equal to 1, and value of Z is as per our original question was 3x1 plus 5x2. So 3x1 plus 5x2, let us write here 3x1 plus 5x2, it comes out to be 3 times 0 plus 5 times 4, which is equal to 20, which indeed is the value that our tableau is giving. So hypothetically speaking, if we would have ended up with one more negative value here in one of the coefficients, that particular variable will enter into the solution, and these iterations will continue until all the coefficients in the last row becomes positive, and hence that is where iterations will stop. So we can conclude that since all the coefficients in the objective function row are non-negative, the current solution indeed is optimal, and these are the values that we get. And you can check for yourself that while achieving this solution, none of the constraints in our problem has been violated. So we end up with two basic variables in our final solution and two non-basic variable in the final solution. Also now notice that it is not necessary that slack variables have to be rendered to be exactly 0 when we are dealing with inequality constraints. So if you have learned linear programming problems earlier, sometimes you may think, oh, then how we can, this is an admissible solution. This is an admissible solution because both the constraints that we had, that is x1 plus x2 less than equal to 4 or 2x1 plus x2 less than equal to 5, both of them are satisfied. S1 and S2 are both greater than equal to 0, and X1 and X2 are both greater than equal to 0. Z takes the value of 20, and there is no further corner point or extreme point to which you can go and improve this particular solution. So this indeed is a feasible solution, and so on. So there are certain special cases in simplex method that we should also look into, that how to do break ties, for example. Now when you are updating the tableau, you have to decide what is the entering variable and what is the leaving variable. Now in some cases what may happen is that multiple non-basic variables may have same most negative or most positive coefficients depending upon how you are setting up a problem, as a maximization problem or a minimization problem. Also, what could also happen is that when you are deciding the leaving variable, it may happen that the minimum ratio test also yields the equal ratios for multiple basic variables. So you have to decide a tie to prevent the cyclicity, that is the same variable is leaving and same is entering in the next cycle and so on. Then your algorithm would be stuck somewhere, and it would take a lot of time to get out of that solution, which is certainly not optimal. To take care of that, there is a very simple rule, what we call as bland rule, that help us decide how to ensure that we break this tie. It simply says that always choose the variable with the smallest index whenever tie occurs into the system. So this also ensures that algorithm progresses towards an optimal solution without cycling, and there is a system involved. So for example, if both x2 and x3 are tied as entering variable, we would select x2 because 2 has a smaller index. It just gives us a systematic approach to take care of that ties are broken systematically and not just randomly. Also, there is another case that arises in simplex method, what we call as degeneracy. What happens in degeneracy is that a basic variable takes on the value of 0 in the basic feasible solution. So, for example, the right hand side becomes 0. Now, the problem is that if you slightly increase there is no scope for increasing the value of this entering variable or non-basic variable, because your basic variable is already stuck at 0. So as a result of which the minimum ratios also become equal to 0, and algorithm may enter a loop and revisit the same basic feasible solution again and again. And this is again where the Bland's rule help us to get rid of this tie if there is multiple degeneracy in the solution. Sometimes what can also happen is that we may have an unbounded solution in linear programming problem. One simple way to think about this unbounded solution is that, let us say we say that you have to maximize 3x1 plus 5x2. Maximize 3x1 plus 5x2, and you are only given one constraint, that x1 should be greater than equal to 0 and x2 should be greater than equal to 0, and no other equality or inequality constraints are given. Now it is very clear that if you make x1 to be infinite, nothing can stop you because there are no constraints limiting value of x1, so your maximum value would come out to be infinity. In that case, we would say that your objective function can be increased indefinitely without violating any of the constraints. Now this is a very simple example where your constraints have been simplified only to positivity constraints. We may have other such situations also where constraints are listed, but they are not preventing your solution to scale up to all the way to infinity. So rather than preventing unboundedness, understand that not limiting your objective function to grow if it's a maximization problem, or diminish if it's a minimization problem. So what happens is that we detect the unboundedness and we find that if all coefficients in pivot column are less than equal to 0, then you cannot do the minimum ratio test, because for minimum ratio test we need to have RHS divided by the coefficient in the pivot column. But this ratio can only be taken if these coefficients are greater than 0. If they happen to be less than 0 and all of them happen to be less than 0, then it is guaranteed that there is an unbounded solution that is present, and minimum ratio test cannot be performed, because nothing is inhibiting or forcing your variable to hit 0 when one of the non-basic variables as they enter into the system are increased. So far, we have actually converted our inequality problems into equality problems by introduction of slack variables and solve the problem. However, if the original constraints are actually listed as equality constraints and then we are asked to solve them, it becomes indeed more complex than the inequality set of problem itself. So in case of Lagrange multipliers or Lagrange function, we learned that solving equality problems were much easier or straightforward because there was no constraint on lambda. On contrary, in case of linear programming problems, solving the constraints where exact equality is involved, in fact, is more tricky, as now we have to look into linear programming or simplex phase 1 followed by simplex phase 2 while dealing with the originally stated equality constraint, because now introduction of slack or surplus variable is not possible because there is no slack available, as you have to meet the constraint exactly at a point. So in our subsequent discussions, we will discuss how to handle these equality constraints with help of an example.